All right, so now we're on to 7.8, which is ideal gas law. Okay, so temperature is supposed to remember that's the average kinetic energy of the particles. Average kinetic energy of the particles. Which is a fancy way of saying how hard these suckers are going, right? How fast they're going, how big they're going, how much stuff can they do when they slam into something. That leads us to the next idea. It's called pressure. Pressure is our force per unit area. Okay, force per unit area. So why would there be force? Well, imagine you got a steel plate sitting here, and you got particles slamming into it and bouncing off, which is exactly what happens, right? Because particles don't only stop when they hit a wall or something. So they're hitting this thing left and right. And so the amount of particles striking this little plate determine how hard they're pushing on the plate. Okay? So pressure is caused by gas colliding into the side of the container and frankly colliding into other gas particles and other things. Okay? Pressure is going to be measured two ways for this class. It's going to be measured in pascals. Okay? Pascals. Pascals are a teeny tiny unit and super annoying. The other way we're going to do it is 1 atmosphere. To give you perspective, at sea level under normal conditions, 1 atmosphere is equal to 101,300 pascals. Okay, so these are just units to measure how hard the gas is pushing on something per square centimeter, meter, inch, whatever. Okay, moving forward, I have pressure versus volume. So if I were to heat something up, okay, let's say I have a container of gas, little metal container. I put the lid on top, and I have temperature, and I'm heating it up. What's going to happen to the pressure inside? Well, the pressure inside is going to get more. Why? Because the particles are going to slam into the side of the container more, and as they slide to the side of the container more, they're going to push on the side of the container more. And frankly, if you have a sealed container and you put enough heat on it, it'll eventually explode of gas. And so the formula that makes that happen is I have pressure over temperature equals pressure over temperature. Now, the way this formula works is we got pressure initial at the very beginning, temperature initial at the very beginning. These little zeros down there mean initial. We say not when we're talking about them, but that's a pressure at 0. Time equals 0. As this temperature goes up, in order for this number to stay the same, because it can't change because that's the original situation, the pressure must go up. In other words, if I'm dividing by a bigger number, I need a bigger number in order for the number to stay the same. So that's straightforward. Now, it's not really clear if that it's not really important to understand exactly how the mechanics of that work, but that's why we write the formula this way. Okay, so I got temperature versus volume. So let's say I have a bag of air, and I heat it up. What happens to my bag of air? Well, it generally gets bigger. Okay, and so my formula is going to look just like that previous. So V naught over T naught equals V over T. Okay, so that means that is a formula looks exactly the same way. As I increase the temperature on the bottom, my volume would have to go up in order for everything to stay the same. Okay. The last one on our list is pressure versus volume. If I take a container and I skish it, the container is likely to get smaller, right? The amount of gas is going to get smaller if I squish on it. Like I take a balloon and I squeeze it, I can make it smaller. And so this has got to be the other thing. So the other thing would be I got P naught, V naught equals therefore PV. In other words, when one of these goes up, let's say pressure, the volume can go down in order to make this be the same, right? So if this doubles, then the volume's got to go by 1/2, right? It shrinks to 1/2. Okay, and so that's the basic ideas about what runs the gas laws, or the gases, right? Makes the gas bigger, smaller. This only works, by the way, for gases that are fairly normal gases. They're just particles sliding on the side of the container. If I squish it down twice as much, I end up with half the size volume. Okay, and that's because they're not attached to each other. Remember, the molecules are not attached to each other. So if I push on them really hard, I can push them closer together. Okay. All right. Let's move on to the next thing, which is kind of more important. Okay, if you put those laws together, you get one big formula. The formula looks like this. And again, it only works when you're dealing with gases that act fairly normal. They act like billiard balls, if you like, slamming into each other. The pressure times the volume original divided by the temperature original is equal to pressure times the volume divided by the temperature on afterwards. Okay, so if I increase the volume, my temperature might go up or my pressure has to go down. One of the two things has to happen, right? So temperature note, it says here that temperature note. So we can't use degrees Celsius for this. Why? Because at 0 degrees, we'd have zero temperature, which means to have zero pressure and zero volume, which happens, by the way, if your gas slows to a stop. The problem, of course, is that's not what happening at 0 degrees Celsius, so I'm stuck with changing this to Kelvin. So it must be in degrees Kelvin, otherwise your formula for sure will not work at all. So I'm going to give it to you in degrees Celsius with what everybody does, and you have to be the person that converts it. Okay, so here's the first practice problem. It says a volume of 5 meters cubed of neon gas was expanded until its volume becomes 12.5 meters cubed. The original pressure was 2 times 10 to the 6 kilopascals. What's the final pressure of this gas? Okay, so here we go. We go P naught V naught over T naught equals PV over T. My initial pressure was 2.00 times 10 to the 6 kilopascals. My initial volume was 5. And now I'm missing temperature. We'll go back to temperatures in a second. Pressure at the end, I don't know, but it's what I'm looking for. It's okay, I don't know that. My volume is 12.5. And again, what about my temperature? What about my temperature at the end? We're going to assume, if I don't mention temperature, that means the temperature is not changed. And what if it was 100 here and 100 here? I could multiply both sides by 100, which is what your math teacher would tell you to do, and it would go away. And since it would go away, anytime I don't give you one of the variables, you simply don't put it down. You simply ignore it. And if you need comfort level, you can look at the previous stuff we did and see that PV equals PV is actually a formula. It's one of the formulas we did. So therefore, I don't need temperature as long as temperature is not changing. If temperature is changing, you definitely need it. Okay, do a little math over here. I get 1 times 10 to the 7th equals 12.5 P. I take my 1 times 10 to the 7th, divide it by 12.5, and I get 800,000. And then the question is, what two things? First of all, significant digits. I've got everything's good to 3. Yes, everything's good to 3, so I need to put a line over that. And the second thing that's kind of key is this. It's like, what units do I use? Well, the good news is whatever I put on the left side, I have to have it on the right side to cancel it out. So if I start in kilopascals for pressure, I use kilopascals over here. And that would be my final answer. All right, let's try the next one. The next one should be very similar sorts of thing. So you try it first, hit pause button. I'll give you some time. Hit the pause button, and then when you're done, turn it back on. Okay, starting that problem. I got P naught, V naught over T naught equals PV over T. And I put my P in, and I get 236 kilopascals. Next problem I would have is what's my volume? My volume is 60.3 all over. Oh, I don't have temperature. I'm going to ignore that. So what's my pressure at the end? 354. And then my volume is what I'm looking for. Good, I got everything I need to know. 60.3 times 236 divided by 354, and I get my volume is equal to 40.2. Again, my units for the left side was meters cubed. My unit for the right side, therefore, has to be meters cubed, and I am done. All right, I'm going to give you a moment. Try your turn, number 5. Try that problem out before I do it, because it's got a very special message waiting for you. So hit pause, and okay, I'm back. All right. Unpause me, you got it ready. Here we go. Okay, I'm going to go P naught, V naught over T naught equals PV over T. You know the drill, it's a gas. It's changing back and forth, so therefore I can use this formula. The ideal volume is 30. It does nothing about pressure. Uh-oh. Well, good news is it doesn't say anything about pressure. I'm going to assume the pressure stays the same, so I can ignore it. So the volume's 30 to begin with, over, what's my temperature? 273. Wait, what? It's 273 because you can't use Celsius. So the way you do that is 0.00 plus 273 gives you 273. Aha! That's equal to my volume at the end. And then 139 plus 273 is 2 carry the 1, 412. 412. Now I noticed this year a lot of people like to cross multiply, so that's what we're going to do. We're going to multiply 412 times 30 and 273 times V. 412 times 30 is 12,360 equals 273V. So then I divide by 273, and I get my volume at the end is equal to 45.3. Check my units, liters, liters. Bam. All right, that's it. Okay, from that you should be able to do the rest of the worksheet. Have that. Come see me if you got a problem.